Fine. Well, thank you very much. Thank you for giving me the opportunity to present our work. As you've seen, I've learned some Polish these days. So the title in the Book of Abstracts was wrong, but it was numerical treatment of atom ion pair in spatially displaced traps. If you understand it, that means you've also improved your Polish command, so congratulations. I've also learned something these days, which is that you love eating quite a lot. I think you've overestimated our abilities to eat these days. And something quite funny that I don't know if all of you have seen it, but there's a dinosaur next to the building, which is quite amazing. It's the first time that I see something like that at university. So, well, going back, I think we've heard many times the advantages of combining cold atoms and ions. So I will explain you our work first. I mean, the theoretical challenges that we have to deal with. I mean, if you're experimentalist, you might not know them, but those of you who do simulations might have similar problems. The method that we have developed, which is an extension of a previous one to study these kind of systems, just a couple of figures with the results and a brief summary. And so we've started with many-body this morning. Then Tobias told about the three-body problem, and now I will only use two-particle systems, right? So the next talk will be by Rosario, so probably just one, and then the conference will be over. No, hopefully not. So what we want to do is develop a method to solve, to study these kind of systems, right? With two atoms that are confined in two different traps that are separated, and solve the Schrödinger equation in 3D. So that means in total we have 6 dimensions, right? And the problem is precisely the interaction between the two particles, right? So, I mean, we've applied to atom-ion systems, but in general, we want to be able to also study other systems like optical tweezers, where people are able to move particles around and place them at any place they want. So to begin with, again, now we have a neutral atom and an ion, and I mean, when one has to do simulations, there are 3 problems in this case, right? The first one is, again, this the interaction potential that is not as short range as in ultracold samples, and then you cannot use a contact potential to model it. So you really have to be able to take this kind of long range behavior. Then another problem is the different ranges of your traps and the interaction potentials, right? So the interaction potential is rather long, but it is still very short compared to the traps, right? Like 2-3 orders of magnitude shorter, and that when you want to solve Schrödinger equation is very demanding. And finally, well, I mean, in this particular case where we have an atom and an ion, typically the frequency of the ion trap is much larger than that of the atom, and that introduces a coupling between the center of mass and relative motion that makes things more complicated. Okay, so we've done. I mean, what we have done works only if we have if our potentials are separated in the different dimensions. So we don't have, let's say, X and Y couplings, which is a reasonable assumption. And just as a matter of doing things simple, we assume that we are separating our traps always along the z-axis. And we do it because then the eigenfunctions, well, the system belongs to this symmetry group, C to V, and then the eigenfunctions have certain symmetries. And if you use an adequate basis set that takes into account those symmetries, then you get a block diagonal Hamiltonian matrix that can be solved more easily. Okay, so again, 2 particles. So this is the 2-particle Hamiltonian. We have kinetic energy, then the trapping potentials, namely optical traps, radio frequency, whatever, and then the atom-ion interaction. And again, the problem here is this term here that adds a coupling between the positions of the 2 particles. Again, it is a 6-dimensional problem, and we describe this atom-ion interaction using an ab initio potential, right? But in general, I mean, if let's say we have 2 electrons, we could put a Coulomb potential. If we have any other kind of interaction potential, we can still describe it. Okay, the way we describe the potentials is, in principle, we could use any one, but at the end, to put it in our machinery, we have to describe it as a polynomial, right? And so that means, for example, if we want to describe an optical lattice, we can only go up, let's say, describe 1, 2, maybe 3 wells, but not more, because at the end, the polynomials diverge towards infinity or minus infinity, and then we are not able to go too far. But in this case, if we have just two single wells, then it's okay. So it's not a problem. We can describe it using just a Telex function along the minimum, or making a fitting of the potential, or any other thing. But once we've got it, we go back to the Hamiltonian, and we can change to center of mass coordinates. And then the Hamiltonian reads this way, right? We can split it in 3 different terms. One that describes the center of mass motion, the relative motion, another term that may appear or not, which is associated to the coupling, which is the problematic part here between these 2 coordinates, right? And to solve to calculate the eigenfunctions, we do it in 2 steps. First we change to spherical coordinates, and we calculate the eigenfunctions associated to the center of mass and relative motion. We call them orbitals, as chemists do. And for this purpose, we use a basis set formed by B-splines and spherical harmonics. Then we take these eigenfunctions, and we put them. We construct a new basis set, a configuration where the total Hamiltonian is diagonalized, right? I mean, this second step might be necessary or not, depending on whether you have this coupling term or not. Right? If it is absent, then you only need the eigenfunctions for the relative motion, because the center of mass only adds some energy levels, right? I mean, it moves your spectrum to higher values. Okay, so these are the essentials. I mean, I do not get much into the details, but just think about center of mass, relative motion, 2 steps, right? And that is the main idea. So we've done 2 different kind of studies. The first one is moving the traps one to the other and see what happens, something that was studied also by others like Antonio Negretti. And also study different situations where both particles are found at the same well, same position, that is harmonic, and this unharmonicity introduces a coupling between the center of mass and the relative motion. These are the 2 situations. Okay, to begin with, the simplest thing to do is to study 2 traps that have the same frequency. Of course, in reality, the ion frequency might be larger, but to start to think whether things work or not, we start it this way. So in this case, the Hamiltonian looks like this. So if it is harmonic with the same frequencies, then you do not have any coupling between the center of mass and relative motion, and you only have to study the spectrum for this Hamiltonian, right? Because that contains all the essential physics. And this is what we get. For example, this is the relative energy as a function of the separation distance. So when the 2 traps are very separated, we get the energies for the harmonic oscillator, right? Which are the ones that appear here. And when they come close, then the 2 particles start to interact, right? And here we have two different families of states. Let's say they are not plotted, but very low here for, let's say, I don't know, maybe minus 1,000 energies. We have deeply bound states where the atom and the ion form a molecule. These states here correspond to trap states. And in this state, this is an interesting one, is the least bound state, right? And if you can see, at 0 separation, the energy is minus 1.7 more or less. And as you increase the separation energy, it goes upwards, right? And it interacts with the higher lying levels, right? So due to these avoided crossings. Now, this is for this scattering length, 2000. It is repulsive. If we make it more repulsive, then this bound state will not be that deeply bound. And this is what is observed, right? It comes closer to the origin, to 0, to the dissociation threshold. And then the avoided crossings become wider, but essentially it is the same kind of behavior, right? Interacting area here and a non-interacting region here. Okay, so 2 traps, we are using same frequencies, so there's no coupling between the center of mass and relative motion. And and before moving to the next situation, the question is, why do these avoided crossings appear? They are produced due to trap-induced resonances, right? So what is happening here is that when the two traps overlap, they are not separated. We have this kind of effective potential for the relative motion, one that Peter showed before. But when the traps start to move and separate one from the other, we get this barrier here, and then this trap state can become resonant with the bound state, and this situation is where the avoided crossings appear and where the exchange of the wave function shape can take place. Okay, now we'll not get much into the details of this other situation where we have the two particles at the same well, but again, the idea is exactly the same, right? So we take any potential. In this case, it's an optical lattice, so let's say sine squared potential. We try to expand it into around the origin, then we get a sextic trap, for example, and we compute the eigenfunctions, right? In this case, the relative motion spectrum looks like this. But due to the center of mass and relative motion coupling, if you look at the total spectrum, then it is not as simple as the one before. But you get, I mean, again here, you observe avoided crossings, right? In this case, the origin of these avoided crossings is different. It is produced by the coupling between the center of mass and the relative motion. And this allows you, I mean, it has allowed to, in experiment in Zelling-Joachim's group to create coherent molecules, right? And the idea is to transfer energy from the center of mass degree of freedom to the relative motion degree of freedom. Okay, and again, you observe this change between the wave functions. Okay, well, this is exactly the same. Just a picture to show this. So this is, I've said it, and again, I mean, this coupling does also appear. I mean, if you take your Hamiltonian and you make the maths there, you can also observe it even when you have two harmonic traps, right? If they have different frequencies or you have different masses, then there's always this coupling, right? And the stronger it is, in principle, the wider these avoided crossings are. In summary, so we have developed this new method to solve the Schrödinger equation in 3 dimensions using ab initio potentials to model the interaction between two particles. We have studied trap-induced resonances, which appear also even when you have two harmonic traps. We have also studied inelastic confinement-induced resonances that exist always every time you have a coupling between center of mass and relative motion, which can also happen in the harmonic case. And with this, I'm done. So thank you for your attention.
Great, thanks. Renee, and then Olivier.
I do theory. I don't know. Yeah. Yeah, but in principle, I mean, if you can model your potential using the harmonic trap, I mean, that's what we would do. But I mean, I don't know how one could do it experimentally. That's your. Yeah, sure. Yeah. Mm-hmm. Yeah. Maybe that's for the network an interesting thing to do. Yeah.
Yes, just on your first example that you treated, just I'm not sure that I got exactly the intuitive picture of that, because we see the trace of that state which is crossing.
Yeah.
Why does it come that way following this parabolic, trace along all those bond states? So can you?
Not really, but apparently, I mean, yeah, it has that kind of behavior somehow. So it's like.
But what I'm saying is that what do we see? I'm trying to understand on this simple thing. Yeah.
Yeah.
Yeah. For instance, yes. what do we see when the distance decreases? We see it looks like you have this one energy level coming from the top, which is crossing all the others.
Yeah.
The trap.
Yeah.
And I'm not sure that I understood the nature of that energy level, which comes down this way. This is what you said. I mean, you said that this black line is something like the last bound state or whatever, but I'm not sure that I got that point.
I mean, if you, what's going on? I mean, truth be told, I don't know, but somehow if you I mean, it increases somehow this way, but I cannot provide you an explanation. But it increases,
I mean, the result is very neat. I mean, you have a flat thing, something which is crossing.
Yeah.
So you like to say, hey, I mean, this is quite simple to understand, but I cannot get who is who in this picture. That's my problem.
I mean, I know. I mean, you can use it just to predict. I mean, if you make that assumption, that I mean, you need to measure this energy, but then you, since it has this kind of behavior, you add that term, which would be like the reduced mass. I mean, the energy for the reduced mass of your system in the harmonic case, and so you can predict this way the position of these crossings by making this. Yeah, but
okay, maybe you can discuss more that.
Thanks. Johannes and then Christoph.
Hi. So I remember there are essentially, I saw almost identical plots and calculations like 15 years ago, Tommaso Calaco and his team. Also the setup, so I can't tell the difference. So can you help me? What is new here? What is different?
I mean, essentially the atom-ion interaction, because we use an ab initio potential. Whereas, if I'm right, I think they used quantum defect theory in their case. And I think also some of the works are 1D, not 3D. 3D? Okay. Mm-hmm. Mm-hmm.
So comparing your results then with theirs, is it does it match?
We get the same. Yeah. I mean, we get more or less the same results. Yeah. So there's not a difference.
So I'm part of this team which produced a lot of these plots, not 15 years ago, but like 5. Yes, so I expect regarding to your question that on this scale there will be absolutely no difference, because quantum defect theory on these large length scales, it absolutely coincides with the ab initio potential. There would be differences at much lower separation. And regarding because I just wanted to comment on Oliver's question, this parabolic state is just the bound state, which has an energy shifted by the parabolic term. If you just write the Hamiltonian, it has a term which is 1/2 mu omega squared d square, where d is this separation. So it's just an offset of the bound state because a bound state climbs the harmonic potential. This weakly bound state of the atom-ion potential. This most weakly bound state, the black one, it's just continuous and anti-crosses with the trap levels, of course, but essentially it's just as it climbs
this one here,
the harmonic potential. Yes,
it moves from this energy to this other energy.
Anything else?
Did you take into account the symmetry of the system? Because like there are two.
Say that again.
The symmetry, that there are the same nuclei, right? So that in fact there are two indistinguishable particles. And did you take, because I don't know, maybe I missed in the model, or like you treat this lithium and lithium ion as distinguishable particles or not?
We assume they were distinguishable. Yeah.
Okay, but in general, there should be somehow this kind of symmetry included.
Yeah, I mean, I don't know what was, which was a problem. I don't remember. But somehow when we used identical particles, there was something odd in the result somehow. Like I didn't remember what. That's why we had to assume that they were distinguishable.
All right. So let's thank everybody again and go to coffee.
So one technical